Welcome to this session. This session is the beginnings of our unit on thermodynamics, with the first part of it being thermochemistry. It's going to deal with things that you hopefully had some exposure to in your first year chemistry course. God forbid you're doing this as a first year course because it's a lot of work. So I'm glad you're here. My name is Renee McCormick and I'm with the National Math and Science Initiative, as you can see by this logo up here on this document. And you most likely found me through our wiki page, which is apchemistry.nimsy.wikispaces.com, and that's where you can find a printout of these lecture notes. They have been edited recently, so I've fixed a few typos. If you've printed them off prior to today, which is November 4th, 2010, then you may have some errors. And I'm going to tell you there's still one more typo even in that file I didn't find until I got ready to do this recording. But we'll fix it as we go along. So welcome, and let's get started. This particular unit has a lot of new terms for you. There's been some studies done that basically say that a freshman college course, which is what you're in, whether you know that or not, but a freshman college course in one of the sciences, whether it's biology, chemistry, or physics, actually introduces more new and unique vocabulary to students than does a freshman college foreign language course. How sad is that? So in order for you to be able to keep things straight, there's a beautiful list here created by a friend of mine named Lisa McGaw. And Lisa did a great job of writing the intro to this unit of notes, and she did a really good job of making nice, clean, easy to remember definitions. So we're going to go through some of those. So energy. I bet you know that one. You've probably known since about third grade. That is the ability to do work or produce heat. In our case, the ability to do work is what you learned first. And in our case, most of that work is going to be done by gases as they expand, or containers that are flexible and can expand, because even if you warm an aqueous solution, it may expand upon heating. So energy for us is also the sum of all the potential and kinetic energy in a system. So kinetic energy is still related to temperature, because temperature is defined as the average kinetic energy of the system. Potential energy, I need you to start to think of as the energy in bonds, chemical bonds. I know you think only in terms of gravitational potential energy, because that's what we've drilled into you for the past several years in all of your science classes, but indeed we have potential differences that occur with pluses and minuses, like in the terms of electricity, like you saw in the electrochem unit, or we'll see in the electrochem unit. But for us, in this unit, we're talking about bonds. So we'll end this discussion with how much energy it takes to make and break bonds and how that affects the overall heat of the reaction. So we talk about this quantity called internal energy. Internal energy is given the symbol E, go figure, and often we can only talk about changes in internal energy, so you're going to see us work some problems with that. I gotta say, your book does a bit of overkill on this concept. The AP exam doesn't go into as much down and dirty detail with changes in internal energy as does your book. So that's the good news. We're going to go through it, but I'll try to kind of guide you along the way of, yeah, this is super duper important and you need to know it, and this is just nice for you to know to enhance your overall understanding. So better definitions: potential energy, like I said, usually in chemistry, this is the energy stored in bonds. So when gasoline burns, there's going to be differences in the attractive forces between the nuclei and the electrons in both the reactants and the products. Kinetic energy, though, is the energy of motion as you first learned it. And so we're talking again about particles and the fact that that kinetic energy is proportional to the average Kelvin temperature. Or I'm sorry, the average kinetic energy is proportional to the Kelvin temperature. I said that backwards, so sorry. Kinetic energy depends again on also, in a mechanical sense, like physics sense, the mass and velocity of the object. So it's not that uncommon for kinetic energy equals 1/2 mass times velocity squared to show up here. And I remind you, from a units point of view, that everything to do with energy is measured in joules. And if you've been given old problems with calories in them, then there's 4.184 joules per calorie. So then we get into some of our laws. This particular set of notes is going to deal solely with the first law and all of its permutations. Those are not the same as perturbations, not the same as perversions. So in all its permutations, the law of conservation of energy, where energy is never created or destroyed, it can only change forms, which means that the energy of the universe is constant. And it's also called the first law of thermodynamics. So one down, a few more to go, but you really already know the first law of thermodynamics is stated in words as the law of conservation of energy. And we'll talk in a few minutes about how it's stated in math. All right, so heat. Heat is given the symbol Q, as in for quantity of heat, the way you saw in electrochem that Q can also mean quantity of charge. We often use Q, a baby Q, as a quantity because we run out of letters. We only have 26. Transfer of energy in a process is what we really can measure. We don't have any heatometers in our laboratories, so we have to measure things like temperature in a final state and an initial state, and then subtract and get the delta T, and then throw it into another calculation where we can calculate through Q equals MC delta T, which hopefully you learned in first year chem, that the amount of the quantity of heat that's transferred is dependent upon the mass and the change in temperature, and a constant that is indeed unique to any piece of matter that you do this with. So with heat, we talk about the transfer of energy, and it always flows from hot to cold. The phrase heat rises, I'm from Texas, and we talk, we get really hot here in the summer, and you walk into a house after coming home from a hard day's work, and if you haven't had your air conditioning set on super duper cold because you've been trying to save some money in energy dollars, then you come in and you can tell if you have a two-story house when you walk upstairs, it's way more warm than when you're downstairs. And so there's this phrase that makes me crazy that we use down here. It says heat rises. Heat does not rise. Heat does not sink. Heat simply goes from hot to cold. The problem is that air carries thermal energy with it. And as air is heated, it expands. If it expands, it becomes less dense. And less dense air floats upon cooler air, carrying the heat with it. So heat doesn't rise. Heat goes one direction. No up, no down, no right, no left, no back, no forth. It goes hot to cold. And that's the end of the story. But when you're in reality living in an environment with air and you warm air, that expands and thus it floats and it carries thermal energy with it. So indeed, if you climb a ladder, you may be able to detect that the air at the top of the room near the ceiling is warmer than the air down at the floor of the same room. All right, so temperature is not a measure of energy. People mess those things up all the time. I watched a professor in graduate school actually make a room full of grown-ups cry over the simple question of define temperature for me. And what he wanted was temperature is a measure of the average kinetic energy of molecules. And people kept saying answers like, it's the amount of hot, it's the amount of cold. Then they tried to get fancier with that, say, well, it's the degree of thermal energy. No, it's simply heat. Temperature is simply the amount of kinetic energy, the average kinetic energy in a system. Heat is a transfer of energy. It's again about energy. Speaking of energy, we have more. Enthalpy. Enthalpy is a word you may or may not know. Enthalpy deals with delta H, which so you may be more comfortable with the symbol. And then we love our subscripts. So we can have the enthalpy of a reaction, which is an ordinary chemical reaction. Heat's either absorbed or released, most likely, in that reaction. Very rarely is it zero. The enthalpy of combustion, which means you're going to burn something. You're going to react it with air. If you've been doing your net ionics, you know there's many different ways to basically get across the idea of a combustion reaction. But we can combust things other than just hydrocarbons, so we can combust all sorts of things that make oxides as a product of whatever we've combusted. The enthalpy of formation is a very, very handy one to know, one worthy of memory. We put the little F on there for formation, and heat is absorbed or released when 1 mole. How much? 1 mole. One more time. How much? 1 and only 1 mole of a compound is formed from the elements in their standard states. So when you use heats of formation, you must use them carefully, proportionally, and understand that the delta HF is given for how much? 1 mole of a compound. Enthalpy of fusion. This is the heat absorbed to melt 1 mole of a solid to a liquid. So if you have H2O solid and H2O liquid, those little double arrows mean they are in equilibrium together when the melting is actually happening. don't want to plant any misconceptions for future units, that the amount of energy that goes back and forth in this process is the delta H of fusion, where we're fusing the liquid state into a more structured solid state. That's where the words come from. The enthalpy of vaporization, the word probably makes more sense to you, delta H vap, we often say. And that is the heat absorbed to change 1 mole of liquid to gas. So I could also do this. And that would have a separate delta H for it. So this one would be delta H fusion. And we don't put F because we don't want to confuse it with formation. We put FUS for fusion. And delta H vap. And then you would note that if I had numerical values here, I could add them up the way I can add these systems of equations together, where that's a gas and that's a solid, and I would have delta H sublimation as well. That didn't make this list, but I just want you to know it's possible. All right, system. That is the isolated area of the universe that you're focusing on. It could be a beaker. It could be a beaker on a table. It could be a beaker on a table in a room. It could be a beaker on a table in a room in a lab. It could be a beaker on a table in a room in a building. It could be a beaker on a table in a room in a building in a city. You have to define your system is the point. Surroundings is everything outside of the system. That is the rest of the universe. Endothermic, hopefully something you already know. Endo, I know it's spelled E-N, but it sounds like the word you are very familiar with, in, like endothermic, means it takes energy into the system. So you add energy. And a lot of times we're talking about delta H, so the delta H signs are going to be positive. So it's a net absorption of energy in the form of heat, usually by the system, especially if we're talking about delta H. And energy is a reactant. And so that's a good way to think about it. If you had A plus B and it's an endothermic reaction, you should think of heat as a reactant. Exothermic is its evil opposite cousin. So that means exit. Exo is like exit. So it's a negative E. And if we're talking delta H, it's a negative delta H. So when we say the thermic, we're really talking, didn't mean to cross it out, we really are talking about the delta H. State function, that may be a new term for you. A state function is a property independent of past or future behavior. Doesn't matter which road you took to school today, it matters that you started at your house and you ended at school. So there's probably lots of ways for that to happen, lots of alternate routes. Doesn't matter what alternate route you took, it just matters where you started and where you stopped. Your bank account, once you have one, your bank account, how much money did you have at the beginning of the month? How much money did you have at the end of the month? It doesn't matter how much you spent, put back in, took out, gave away, borrowed against, gave someone money, whatever you did, it's how much you started with and how much you ended with that matters. That's a state function. Entropy is a measure of disorder in a system, the measure of chaos. That's going to be a big thing we talk about in the next set of lecture notes that we cover, the thermodynamic portion, along with delta G. But you've seen delta S and delta G before if you've been traveling along the NIMSY pathway where you've already done electrochem. And so delta G is basically the amount of free energy to do work. And delta G, I remind you, equals delta H, our enthalpy term, minus T, our Kelvin temperature term, delta S, our entropy term. And we're going to get into serious details with that in the next couple of recordings. Work. You first learned work as a force acting over a distance. So in physics, that's what work equals. In chemistry, we use a baby W for work, just to make you confused, because in physics we often use a big W. But the baby work is going to be defined in different ways. So the work that we do most often in chemistry, think test tubes and beakers and such, is going to be about expanding and contracting gases. So if the gas expanded, it did work on the surroundings by moving the walls of its container. If it was contracted, then the universe did work on the container and moved the walls inward. So expanding would be that work left the system, and contracting would be that work was done on the system, because all of these signs come from the system's point of view. So you got to put yourself inside the system. So you got to be inside the beaker. Standard conditions you already know, that's called STP. Now, STP is standard temperature and pressure, which is 0 degrees Celsius, and humans are not happy lab workers when you put them in a laboratory for very long at 0 degrees Celsius. So we talk about standard conditions. So this, you got to pay real close attention to the word that follows the word standard when you're talking about temperatures and pressures. So standard conditions are defined as like laboratory conditions, which are 1 atmosphere pressure, so that human eardrums are not imploding or exploding. 25 degrees Celsius, which is far more comfy than 0 degrees Celsius. And if solutions are involved, we're going to standardize those at 1 molar. And all of this information is communicated very, very effectively by adding the little naught, N-A-U-G-H-T, British pronunciation, naught, for 0. So that little degree symbol, or naught, can be added to any one of these symbols. And when you do that, then you automatically know that you're talking 1 atmosphere pressure, 298 Kelvin, 25 degrees Celsius if you must, and 1 atmosphere of pressure, I think I already said that, but 1 molar concentration. Now, if you're working old problems and looking at old answer keys and stuff like that, you may see a lot of quantities just expressed for delta H as kilojoules, or even joules. But we're getting a little pickier now that we really need to quantify that it's kilojoules per mole. So in some of the stuff that you may have seen from the National Math Science Initiative, the documents that existed prior to, say, I don't know, 2000, maybe the late 90s, but I'm going to say 2000, maybe even 2002, we weren't so picky about it. And I was even taught that the per mole thing didn't matter a long time ago. But it matters now. So we're going to try to get in the habit of doing kilojoules per mole. And you won't have any problem with this because this is new to you anyway. It's me that's going to have trouble with this. So you're just going to have to call me out when I mess up and don't put kilojoules per mole for a delta H or a delta G value. Alright, so let's get into some of the theory behind this and talk a little bit more depth about energy and work. And again, I remind you, we're not really talking so much in chemistry about force times distance work, although we can. We're going to stick more with the work that's done as it relates to heat with expanding and contracting gases. Again, your book goes on about this ad nauseum. We're going to kind of cut to the chase. And we're going to work some simple problems. Then we're going to probably switch over to a different document where I kind of go through this in a little more gory detail, but we're going to kind of diffuse your fears first. Energy and work. Energy, energy is defined as the ability to do work. So for us, energy in the chemical sense is a combination of the heat energy and the actual physical work. So we define energy as delta E. Again, we have to measure final and initial states because nobody has an energiometer in their lab. So delta E is equal to Q, the quantity of heat, plus W, the quantity of work. So the signs for this are what are going to drive you just a little bit crazy in this unit. So the signs of Q are positive if heat is absorbed, or I like to think of it as added because that makes sense to the positive in my brain. I'm a math girl. And it's negative if heat exited or was released. So it's negative if it was subtracted or exited. I like exited because that means exothermic. Alright, so the signs of W then are again from the system's point of view. If you squished and compressed the system, then you must have added work in to make that happen, so we give it a positive sign. But if the system expanded something, like think about a balloon. Think about if you had a balloon full of helium and you dunked it into a serious ice bath, the balloon would shrink a bit. That would be the ice bath doing work on the balloon. But if you took that same balloon and you dunked it into a warm water bath, then that balloon is going to end up expanding compared to what it was at room temperature. And that meant that the system did work on the walls of the balloon, which were flexible and would allow for that, not a rigid system. So we would give that a minus work because the system had to do work, thus it lost energy. You know by now that if you do any work at all, you get tired. So you lost some energy. So when related to gases, work is a function of pressure. So we can redefine work as, just go with me on this for a moment. Pressure is a force per unit of area as defined in physics, and then we also can do this with a change in volume. So the minus sign is important. You cannot neglect it. So work is equal to minus P delta V. Alright, so before I actually do some of these simple little problems, I'm going to take you to the dark side for a minute and kind of recap what we've said so far. All from the first law of thermodynamics point of view. And aren't you glad you are sitting right now in a comfortable place listening to this, hopefully with your favorite beverage, and you need some paper. This is not in the notes. This is just me trying to explain in English and bring some clarity to the situation. What's going on with this so far? Okay, like I said, this particular set of lecture notes is going to deal solely with the first law of thermodynamics. You already know the words for the first law of thermodynamics. It's called the law of conservation of energy, as well as the first law of thermodynamics, interchangeable terms. And you can probably stand up and recite it much like the Pledge of Allegiance. The energy of the universe is constant. Energy cannot be created nor destroyed, but energy can be converted from one form to another. Quote, unquote. I missed a set of quotes, didn't I? Right there. All right, so if you want to state it in mathematical terms, then delta E is equal to Q plus W. In English, that means E is the internal energy of the system. E is a good symbol for energy, I think. Q is the heat energy of the system, so the Q is quantity of heat, not to be confused with Q and quantity of charge in coulombs in electrochem. And baby W is work. For us, when work is done by a system, it's going to be an expansion. When it's done on a system, it's going to be a contraction. We're going to talk about gaseous systems more in terms of work. If the container is rigid, yeah, then that simplifies everything because you didn't have any expansion or contraction, and so work is essentially assigned as value of 0. So the sign conventions, like I said, can get a little hairy, so let's get our heads wrapped around them right now, from the get-go, as we would say in Texas. So the sign conventions are assigned again from the system's point of view. If you assign a positive Q value, that's because you added heat into the system. It got hot. It got warmer. Its temperature went up. The final temperature is greater than the initial temperature. And you need to think about connecting that concept in your brain to the words endothermic. If heat was lost from the system, the container got warm. You could feel it if you put your little hands around the beaker, because heat is being lost from the system, and you can feel that as thermal energy as it was transferred to the glass and then onto your little thermoreceptors in the palm of your hand. So it is lost from the system, so heat exited the system, so the minus sign makes sense to my math brain, and the exo of like exit, the exothermic word even makes sense to my brain. Work is a little more abstract for you because this is a new concept for you. Work, if work is added to the system, we often say work is done on the system in test questions. So if you squished something, you compressed it, you or the surroundings supplied the work to make the walls of the container go inward. If the system made the walls of the container go outward, all by its whittle lonesome, then that we give it a negative sign, and work was done by the system, and that's an expansion. But whether it's Q or whether it's W, it's all about energy, and it's done in units of joules or kilojoules. I know, you probably need to pause and rewind and hear that again. Especially before I move on to this next part. I would listen to that twice, 3, 4, 5 times if you must. Everyone is capable of learning. It comes down to the number of repetitions we need, and that varies pretty much on a daily basis for most of us. So I'm moving on to the next piece, keeping all that other stuff in your head. And we also define work as negative P delta V. And you're wondering why negative. I know you are, because you're curious children. Delta V is equal to final minus initial. That's not a big deal. Delta T, you know, delta anything. When we put a delta on something, we're talking about a final minus initial situation. So let's think about it in terms of this expansion and compression stuff I'm trying to get across to you. I don't know how effective I am. But expansion, we assign a positive delta V, because if you think about the math, if it expanded, wouldn't the volume of the container be greater at the end of the story than it was at the initial? So this is a big number minus a small number. Wouldn't that equal a positive number? Of course it would. So if it's an expansion, the volume increased. That's all I'm saying. Duh. Therefore, minus W. How come? Well, if the system expanded, then the system lost some work because it had to do work. So it sacrificed some of the capability for work that it could do, and the system did the work expanding the container. And the converse is also true, which means just turn all that around. If it's a compression, then wasn't the volume small at the end, the final condition, minus the fact it was bigger. That's what compression means. And so wouldn't that equal a negative number? Of course it would. Therefore, how did it get compressed? Work was added into the system. The surroundings did the work. So the system lost some work. No, that's not right. Let me change that. Work was done on the system. Let me just change that whole little statement right there to work done on system, so that you think of work being added into the system. The surroundings, if it was compressed. You know what, I should have erased that. That was good. Work done on system. Or you can think of the surroundings did the work on the system. Either way, work was added into the system. That's the point with the positive W. What if we're not changing? What if we don't have a delta V? Well, your life just got easy. If you don't have a delta V because you've got this rigid metal container or something and you can't have expansions and contractions, then the delta V term is a big, fat, beautiful, round, symmetrical, plump 0. And work would be equal to negative P times that big, fat, beautiful, plump 0. So it would equal 0 as well. So delta E would simply be equal to Q plus W, which would be equal to Q plus a beautiful 0. And you guessed it, that means delta E would be equal to Q. There might be a point tied to that concept on the AP exam. But there's other exams you're going to face in life, which means you may really need to understand that better. Okay, so again, you may have to back that up. You may have to do that again, especially since I didn't do the best job on the positive W part. Because I'm moving on to the next big idea I got to connect in your brain. Now we're going to try to connect all this concept about this work and this Q to the Q that you already know and love. You already know that Q equals mc delta T. And this little p that I've put on there means at constant pressure, because we can also do constant volume calorimetry. But when we do constant pressure calorimetry, which is what you do in your laboratory 99 times out of 100, because you have open containers. You have open beakers, open test tubes, open coffee cups, whatever it is. We're doing this in laboratory conditions quite often in an open container, which means that the pressure that the whole entire reaction is experiencing is equal to the atmospheric pressure. So we're going to go through some algebra aerobics for me to derive something new for you. So here we go. Delta E is equal to Q plus W. That's not new. We've already said that. So I'm just going to sub in the fact that W is equal to minus P delta V. So that means delta E is also equal to Q plus a negative P delta V. Therefore, Q, just rearrange and solve for Q. Solve for Q. Just pull Q off of this. Q is equal to delta E minus a negative P delta V. That's the same thing as saying that it's equal to the work. So when I distribute that minus sign across the P delta V term, don't I get a positive sign? Isn't minus a positive? So delta E plus P delta V is also equal to Q. So now these deltas I can get rid of if I actually do that the final energy plus P delta V final minus the initial energy plus P delta V final. So I can actually get Q down to those terms. And all of that work is simply to derive the term for you, enthalpy. You've gone on faith at this point. Sometimes you have to ask why. If you don't care why, then just, that's fine. But if you do care, then the term enthalpy, or delta H as we symbolize it, represents the delta E plus P delta V term in both of these expressions. So now we can clean up this ugly E plus P delta V final mess and just simplify it and say, you want the heat of the reaction? No problem. The heat of a reaction is equal to the enthalpy final minus the enthalpy initial, which if you've had this in first year chemistry or you've read anything or paid attention to delta H at all, then you know this already as delta H of the reaction equals delta H of the products minus delta H of the reactants. Or Hess's law, as we're about to discuss, or I lovingly call Hess's law the Big Mama equation. And we can link it back to Q as long as we stay in those open containers. Q then of the reaction is equal to MC delta T. So in a lab setting, we use this a lot because we use a lot of what we call coffee cup calorimetry. And when we do that, it's equal to the delta H of the reaction. And this is worth loads and loads of points on the AP exam, hence this discussion. And I remind you, we love our subscripts. So check all these subscripts out. We can make a solution by taking a solid and putting it with water and making a delta H of solution. We can make a combustion by reacting something, and I remind you, not all of combustion reactions are hydrocarbons. Unfortunately, this example is. It's our good buddy propane. Delta H of combustion, add oxygen, make the oxides of what you combusted, an oxide of carbon, an oxide of hydrogen. Fusion, we've already talked about, and it has partners. There's also delta H VAP, which is going liquid. Okay, let's do it this way. Liquid to gas, and there's also delta H sublimation going solid to gas. That's what carbon dioxide does at room temperature and 1 atmosphere pressure, dry ice. Then we can take and have a reaction. In this case, all of these are solids, which is a bit unusual. And we can have a formation. This is the one you're going to use a lot, and I need you to get your head wrapped around this definition now. How much are we going to make? We're going to form 1 mole, and only 1 mole, of a substance from the elements in their standard state. It's okay to use fractions. You're going to see fractions here a lot. Because in order to form 1 mole, you have to have fractions sometimes. I want to form a mole of water in the liquid form, which is its standard state at room temperature and pressure. So what would I react? What elements make water? Not a trick question. H2 and O2. Both of these would probably be in their gaseous form. And I do not have a balanced equation. So what must I do? I must leave H2s alone. I got 2 on each side, but put a half here. So when you start seeing the fractions in there, you probably have entered the land of delta H formation. These are also the values in the back of your book. The appendix of your text. Okay, so let's go back to the easy calculations. Let's get to the right file. So scary as some of that theory sounds, it's really not. So this is more what you're about to see is more the way we have you calculate with these things. So take a deep breath, and here we go. We want to calculate the delta E for a system that's undergoing an endothermic process. Ooh, what'd they just tell me? Endothermic process. Therefore, delta H is positive, Q is positive. Both of those are positive. That's what endo, heat was added into the system, in which 15.6, now I know it's a positive 15.6 kilojoules of heat flows and 1.4 kilojoules of work is done on the system. 2 sig figs. They just locked me into 2 sig figs. So, delta E is simply equal to Q plus W. What do we know? We know that Q is positive. How do we know? Because endothermic is my friend and tells me heat was added in. So that means this is going to be a positive 15.6 kilojoules. Right? They gave it to me in kilojoules. Yes, they did. Plus the work done on the system. On the system means added. So it's a positive W. So really all they wanted to do was kind of figure out, hey, kid, do you have any clue about the signs on this stuff? Not a hard problem, right? Are you smarter than a 5th grader kind of math? So when you add 15.6 and 1.4, you're going to come out with 0, carry 1, 17.0 kilojoules. So the delta E for that system is 17.0 kilojoules. Now, PV, work, that negative P delta V term, also is work. Work is equal to P delta V. We just put a negative sign on the P delta V. Calculate the work associated with the expansion. Okay, did that mean that work went into the system to make it expand? No, that would make it compress. Expansion means the work came out of the system because the system moved the walls of the container. So that's a negative work. From 46 to 64. Now, if they didn't use the word expansion, if they left this little prepositional phrase out with the expansion, second preposition of a gas. So if they just said, calculate the work associated when the volume changes from, got a whole bunch of prepositions lined up there, of, with, from, then at, another one. So expansion was my key, but even if they just gave me this, can't you tell that it was little to big, therefore an expansion? Sure you can. And a constant pressure of 15 atmospheres. So calculate the work. Work equals negative P delta V equals negative 15 atmospheres. And that's going to be a positive 18 liters. Right? The difference between 64 and 46, if you must. Final minus initial is 18. So that is negative 270 negative 270 liter atmosphere.